Okay, I guess we can start now. So today we are very glad to have Rinon here. Rinon is currently a PhD student at Tel Aviv University, where he is supervised by Prof. Daniel Cohen-Or and Dr. Amit Bermano. His research focuses on generative models, few-shot and unsupervised approaches, and on combining vision and language. And recently, Rinon has been interning at NVIDIA Research, where he is working on personalization of vision and language models. So without further ado, I will pass to Rinon.
Okay, so thank you very much. Thank you for having me. So hi everyone, Rinon. And today I'm going to talk to you about a fairly recent topic, which is personalized text-to-image generation. Okay. And before we talk about personalized text-to-image, let's talk a bit about this fairly crazy thing called text-to-image in general, right? So most of you are probably already familiar with at least one of these, but to get everyone on the same page, we're talking about generative models that take as an input a string of text, for example, a hedgehog using a calculator, right? And they produce an image that matches this thing, for example, what we see here, right? And these things are pretty insane, right? And their compositional understanding is really phenomenal, but there's something missing here, right? What if we wanted to use this amazing power to generate an image of a specific subject, right? What if we wanted not just any teddy bear on a skateboard in Times Square, but our personal childhood toy? Okay. So what if I wanted to take this cat here, for example, which I captured a few images of, and ask DALL-E to give me an image of it as a backpack and hopefully get something that looks like this? Okay. The trivial way to try and tackle this is to try to describe our subject, right? So we tried doing that. We took a bunch of images of simple concepts like this lovely teapot over here. And we asked people on Mechanical Turk to describe them in a way that would allow an artist to recreate the object, right? So it's a very simple model. We can call it pixel to Mechanical Turk to pixel, and we can see how well it works. So here's an example description from one of the Turkers, and here are the images that it recreates. Okay, so you can see that we got a teapot. It's colorful, but that's more or less where the similarity ends, right? What if instead we could teach the model a new word that represents our specific object, right? Say we gave it these few images of the teapot, and we told it, here you go, this thing here, this is a pop nut. And then we could just ask it for new photos of a pop nut. And that's what we're going to learn how to do today. And here's an example of the teapots that we're going to get with this approach. Okay, so it's not perfect, but I hope you agree it's much, much better than what we had before. Okay, and since we're describing the object with a new word, and words are, well, inherently composable, we'll be able to put our object into new context just by changing the sentences that we use in our prompts. Right? So, for example, we could ask for a pop nut watering can and get this image, or we could ask for a manga drawing of a steaming pop nut and get something that looks like this. Okay, and just for brevity, from here on out, instead of cluttering the slides with made-up words like pop nut, we're just going to designate our learning words with this blue S star over here. So I hope the idea is simple enough. We're going to try and teach a model new words. And before we delve deeper into this, I just want to give some credit where credit is due, because this isn't actually the first paper where our NVIDIA team does this sort of thing. We actually presented a paper in ECCV where we taught Clip new words that describe specific objects for discriminative tasks. Okay, so for those of you who don't know, At a very high level, CLIP is a model that takes an image and some text and tells you how similar they are to each other. And you can use it to do many things like open vocabulary image retrieval, classification, segmentation. And in this fluffy work from ECCV, our goal was to teach CLIP new words exactly for these sort of discriminative tasks, right? So we wanted to be able to retrieve an image of our specific toy wagon, but also combine it with text so we could get, I don't know, an image of this wagon on the beach, right? And so the setup is this. We get a small image set with a shared object, again, like this green toy wagon. And we find new words that describe this specific object so that we can then prompt CLIP, for example, in order to find an elephant on this specific toy wagon, and just use some off-the-shelf segmentation model built on CLIP in order to segment this part of the image, right? This specific elephant on our toy wagon. At a very high level, the way we do this is that we predict a new word so that sentences like a photo of our new word will get high CLIP similarity to the images that represent the concept, but low similarity to coarse class text descriptions of this concept. For example, a photo of a skirt and not the specific skirt. Right, and again, this gives us a new word that we can then just plug into downstream CLIP-based models in order to do retrieval, segmentation, and so on. So that was a bit high level, but I hope the general idea was clear enough. And the obvious question is, well, why not just use this same approach for generation, right? And the answer is, it just doesn't work. If we try to plug in these new words into something like VQGAN plus CLIP, CLIP-guided diffusion, things like that, we get things that look like they have some broad semantic understanding of our concept. For example, if you look here, you'll see that most of these images do kind of resemble a mug, but the quality is extremely bad, and it's not exactly our specific mug, right? So we can ask, well, why is this happening? And we think that the reason is because we used a discriminative training task here, right? Our goal only tried to differentiate between this mug and the general concept of mugs. And for that, it was probably sufficient to learn that this mug has black and white colors and that it has text on it. But right, more than that, this type of training doesn't even constrain the new words to regions of the space that correspond to natural looking images. It doesn't really care at all if the best match for the new concept is some garbled mess of an image. All it needs is something that looks vaguely like a mug, it has black and white colors, and it has something that looks like text on it. Okay? So to summarize this in one bold sentence, discriminative training fails to capture our concept. How do we fix this? Well, we can try using a generative task. So we're back to text-to-image models. We're going to work with a specific model, which was at the time the state of the art, latent diffusion model, or a LDM. And I was told their architecture is a bit scary, so we'll just go on ahead and hide it because honestly, it doesn't matter at all for our method. All you need to know is that we're using a diffusion model conditioned on text. Okay, for those of you who are not familiar with diffusion, again, we don't really need to dive too deeply into the details, but the core idea is this. You grab an image and you add random noise to it in many small increments over many steps. And then you teach a network to reverse this process, right? Take a noisy image and remove the noise one small step at a time. And finally, to generate new images, what you do is you just sample noise that looks like the tail end of this noising process, and you clean it with your trained network one step at a time. Okay, and this cleaning network can be conditioned on additional external information like segmentation masks, images, or even text, which is what we're going to use. Okay, so we're going to use a pre-trained text condition diffusion model, and we're going to teach it new words. And for that, we're only going to focus on this part on the text encoder converts our words into conditioning codes for the network. Everything else is going to be kept frozen. Okay, so let's dive into this encoder and see how it works. Okay, so basically, most language models you're familiar with, they start in a similar embedding step. You grab your sentence and you convert it into tokens which represent the different words. Basically, for example, you have the word photo in the sentence. You look at your word dictionary. You see that photo is number 701 in the dictionary. So now you just convert the string into a series of dictionary indices, right? You have the index 701 at the same spot as the word photo. Then you take these indices and you go to a lookup table where you retrieve a vector of numbers, a continuous vector that represents this specific word, right? And these vectors are typically learned as part of the model training. And what we're going to do is we're just going to train a new vector that will represent our new personalized concept. Okay, so every time we see our placeholder string, we'll know to go to the lookup table and fetch our new vector instead of a vector that represents an existing word. Once we have these vectors, we can feed them into some transformer, which converts them into an output that will serve as our conditioning. Okay, so I hope that was clear enough, because actually that's pretty much it. That's the entire idea. We're keeping pretty much everything else frozen, and we're just learning this tiny embedding vector at the input of the text encoder. And we'll see that these text-to-image models are so expressive that this is already enough for many tasks. Okay, I'll take the chance now to highlight that the conditioning code is typically not just a single output vector. It's actually a tensor with a length related to the maximal prop length that our text encoder can handle. So for stable diffusion, for example, there's a clip text encoder that outputs a tensor of length 77. You can think of it as some advanced processing of the input words, right? Where we have one vector representing some information about the word in the context of about each word in the context of the sentence, and padding for everything else. Okay. We're still missing a word about the actual training, but that's fairly simple as well. We're just going to continue the diffusion training as usual, using samples from a small image set of our concept, right? So we'll have 3 to 5 images representing our specific concept, and we'll add noise to them and try to learn how to remove the noise conditioned on a text prompt containing our new word. Okay. And again, the only thing that the training process can change is the embedding for this new word. So this sort of training approach really motivates the model to put as much information about our object inside the word embedding. Right. So again, I hope that's clear enough so far. And let's move on to see what this can actually do. Okay. So let me start out by convincing you that this approach lets us get a pretty good encoding for an object, especially when compared to previous alternatives. So here you can see 2 objects, one of which we saw earlier. And here are the reconstructions using our method and using DALL-E 2, where DALL-E 2 is actually conditioned on a clip image latence. So the way we create these variations with DALL-E 2 is by encoding our training images, right? The images in the top row using clip, and recreating the object by feeding this clip encoding into the DALL-E model. Okay, so you can see that the reconstruction here is worse. And since this is actually completely skipping the text part of the model, right? It's not possible to change these outputs just by playing with our prompts. If we wanted to edit them, we'd need to use something more complex in the case of DALL-E. We've also seen attempts to recreate the objects using text. Here you can see another quick reminder that this just doesn't work, right? It's very, very difficult to describe an object using text in order to get good reconstructions. What sort of things does this approach let us do? Well, it turns out that quite a lot. First of all, we can take images of this stone bird, for example, and put it in watercolor painting, right? Where the goal is to try and preserve the structure of the stone bird, but change the style of the image, right? On the other hand, we can also prompt the model and ask for example, a house made from similar materials to the stone bird, right? So we're not limited to just the appearance of the concept we learned, right? We can really understand more high-level semantics like the materials it's composed of, etc. We can use this approach to unearth ancient mosaics of Furbies. We can put them on death metal album covers, and you'll notice that the model can change the concept's color as well, right? It doesn't have to maintain the same colors as this original Furby if changing the colors will better fit the result. And again, we can really see that the model manages to capture the high-level semantics of the objects. So if we train on images of this red ball, for example, we can later put food in it or have a mouse use it as a boat, right? The model really understands that this is an object that can contain other things because, again, it has seen balls before, right? Okay. We did try to invent some baselines to tackle the same task, for example, using the fluffy approach we saw earlier, or optimizing VQ-GAN plus clip using both text and the target images concurrently. We saw some of these images earlier. The point is these approaches don't really work, right? They don't come close to giving us what we want. Beyond that, I've been talking about concepts, but until now we've only seen specific objects. And actually, this is a far, far more general approach. And you can learn more abstract things like artistic styles and then apply them to new images, right? So we're not constrained to just learning the appearance of a specific cat toy. Right? We can also compose learn concepts, at least to some extent. So we can learn a word that represents this artistic style, for example, and another word that represents our cat, and then ask for our cat in this style. Okay, so these types of combinations work fairly well, but what doesn't really work is trying to put the two objects trying to put two different objects side by side. So if we take, for example, the word we learned from this clock and the word we learned from this cat, and we ask for them side by side, we'll still get things that tend to look like this photo of a clock in the style of the cat. Okay, it's partially a limitation of LDM, which is pretty bad with side-by-side compositions to begin with. It's partially a limitation of our training approach, which basically just focuses on one object at a time, right? But the LDM limitations are already being tackled in new literature, and hopefully soon enough you'll see ways to allow these sort of training approaches to combine multiple subjects side by side at inference time. Another use case is in fixing model biases. So for example, if you take LDM and ask it for stock photos of doctors, you get things that look like this, right? We get pretty much just white male passing images. What we can do instead is we can learn a word that, right? We can learn a new word for doctor, which was trained on a small, well-curated data set of images. Since we only need about 5 images to learn this new word, we can just handpick them, make sure they contain enough diversity, use them to teach the model a new word for doctor, and then just use that instead in order to get a much fairer representation. And last but not least, this also works with downstream models built on top of LVM. So if you have, for example, a model that lets you in-paint a region of the image conditioned on text, then you can use the learned words as part of that conditioning text in order to, right, again, condition this in-painting operation and just add our cat's toy in specific regions of an existing image. Okay. So that was a lot of qualitative results, but we wanted reviewer to accept our paper. So we also had to investigate the properties of this latent space and run some quantitative evaluations. So we'll start by describing the metrics we're interested in, what we're going to use to measure our performance. So let's say we learned the word that represents this clock, and we then asked for a photo of it on the beach and got this image. There are two things we're interested in here, right? First, we want to make sure that our generated images, well, we want to make sure they contain our object, right? So we'll want to look at the image similarity between our generated image and our original training set. On the other hand, we want to make sure that the generated images match our prompts, right? We want to make sure that this is a photo on the beach. So what we can do is we can remove the new word that represents our subject from the prompt, and then look at the text-to-image similarity between our generated image and this conceptless prompt, right? Basically, just make sure that this photo is indeed something on the beach. Okay. So these are the two metrics we'll be looking at, and we'll be implementing them using CLIP. Okay, sorry. So to measure image similarity, again, we'll calculate the CLIP space distance between our generated images and the original training set. And to measure text similarity, we'll use the cosine distance between our generated images and the conceptless text that we use to prompt the model. Okay, so I hope that that's intuitive enough. And here you can see a plot where the x-axis is the text similarity we just described. The y-axis is this image similarity, right? In both cases, higher is better. So ideally, we want to reach a point which is as close as possible to this top right corner over here. Okay, and we can now investigate our space by adding more evaluation setups to this plot. Okay, so you can see where our model is located and how it changes if we adjust the learning rate. But we can also, for example, look at what happens if instead of using a single word to represent our concept, we let the model use multiple words, right? We let it use more tokens, kind of like a StyleGAN's W+ space, for those of you who are familiar. Okay, so you can see that when we do that, we can get better image similarity, but it comes at a cost to the text similarity, right? The images look closer to the original concepts, the training images, but it becomes harder to modify our object using text. On the other hand, we can try to add latent space regularization and try to force our learned words to be closer to real words, to things the model saw during training, right? And when we do that, we see the opposite effect, right? We see that we get better editability. It's easier to change the subject, but they look less similar to the training set, right? It comes at the cost of the fidelity to the concept itself. So we can actually see that there's some sort of trade-off within this word embedding space, right? If we use words which reside closer to the distribution of real words, to things that the model has seen during training, we can get better editability, but it's harder to represent our concept when we're constraining ourselves to this smaller space. On the other hand, the further away we let our model move from this area, right, by increasing learning rates, by adding more words to our prompts, well, we can get better reconstructions, but we're using inputs which are further out of domain, right? They're less similar to what the model knows how to work with, and then our editability suffers. Okay. We also looked at the human captioning in this scenario, and this result actually surprised us. We expected that human captions will perform worse on reconstruction, but we also see that it makes things harder to edit as well. And we think that this is probably because the sort of models we're using, they tend to hyper-focus on subsets of highly semantic words within the prompt, right? They ignore many parts of the prompt. And when you're trying to describe an object, you typically use very long prompts, you use many words to describe the intricate object details. And when the part of your prompt that describes the object is long, then there's a higher chance for the rest of the prompt to be ignored, right? For the model to focus just on the words that are part of the description. Okay. Just to convince you that these clip metrics aren't completely detached from reality, we also repeated this experiment for a subset of our scenarios using humans to score the results. And we can see similar behaviors here as well, right? We can see this trade-off curve where words closer to the domain of real images are easier to edit, but less identity preserving and vice versa. And we can see that text descriptions, right, human captions perform worse on both image similarity and text similarity. Okay. We also looked at a few extra properties, like what are the odds for a concept to be well covered by our prompts, right? Basically, if we just pick a random concept from the internet, what are the chances that we can actually represent it as a word embedding? We also looked at how much cherry picking you should expect. Most of the results we saw so far, we basically generated sets of 16 images, and I'm showing you the best one out of them. So there is some cherry picking involved in that sense. But really, the cherry picking factor you need isn't too bad. If you're willing to generate 4 or 8 images at a time, you have a very high chance of at least one of them resembling your prompt and the text. We also looked at things like how many images you need for training, what sorts of variations you need there. I think these experiments don't teach us a lot, so I'm going to skip them pretty much. If you want to talk about them, you're more than welcome to reach out later or read the paper. I'll be happy to describe the details. Okay, so that's it for LLVM. And now we'll move to another topic, which is stable diffusion. And you can ask, well, why does stable diffusion deserve its own topic, right? Stable diffusion is based on LDM. The models are pretty similar, but it turns out that stable diffusion is a bit of a mess as far as inversion goes. And we're going to talk about why this is the case and cover a few ways in which this can be fixed. Okay, so let's start by seeing the problem. And so we can take our lovely cat over here and try to invert it into stable diffusion using a single word, the same approach we used for LDM. And we'll get these images. And this looks pretty horrid, right? But no worries, stable diffusion has great quality, right? We can try to fix this, for example, by adding more tokens. We saw that this can help us with identity preservation. And indeed, if we do that, we get these results, which are great, I think, right? The color order isn't the same, but you can really see that the model manages to capture the face and the semantics of the cat statue that we're trying to learn. Okay, so that's great. Let's put our cat on the beach, right? So we'll ask for a photo of our cat on the beach and get these results. So those of you who are keen of sight may notice that these results don't really show a cat on the beach, right? There is no beach involved. the images actually look pretty similar to what we had when we just prompted for a photo of our cat, right? This is an overfitting scenario. We can't edit our object. And in broader terms, what we actually see is that for LLVM, it was possible to find some sort of sweet spot on the editability reconstruction curve that lets us have both good identity preservation and the ability to change our object using text. But it turns out that this doesn't really happen with stable diffusion. It's very hard to find such a spot. And you can ask, well, why is this happening? Why does stable diffusion inversion work worse than LLVM? And here I can mostly speculate, but the two main reasons we think are involved here are, first of all, well, basically, stable diffusion changed the text encoder from a BERT transformer that is trained jointly with the diffusion model into a pre-trained clip encoder. Why is this important? Because it means that the text encoder was trained with a discriminative task, right, rather than a generative one. And this could indicate that its latent space is less visual, less likely to care about fine details, and more likely to hyper-focus on subsets of words in the prompts, right? And we already saw that this sort of hyper-focus is a problem when you try to learn embeddings for discriminative tasks, for example, right? We saw the fluffy examples at the very beginning, and we saw that using discriminative training didn't work well for trying to generate images later on. So that's one possible reason here. Another alternative, which is a bit simpler in this case, is, well, simply that the text encoder has a much smaller capacity. LDM's text encoder is almost an order of magnitude bigger than stable diffusion's. It has a much larger embedding space, so it's probably just easier, right? It has more room to capture fine details in a place that is still close to the distribution of real words, a place which is still editable. And we actually think that the second problem is the more severe issue here, because fairly recently, Stable Diffusion 2 came out. And the main thing they changed there is that they're using an open clip text encoder, which is a bit bigger than the original Clips model. It's roughly 300 million parameters. And we didn't examine this quantitatively, but we've seen many reports that inversion does work much, much better with Stable Diffusion 2, right? So it seems that this approach, or inversion approach, is sensitive in a sense to how big the text encoder is, how expressive it is. Okay. So this problem exists, but we can look at a few ways to try and solve it, right? To try and avoid this issue. And we can start by talking about tuning the model. Right, so we said it's hard to get very high identity preservation if you also want to retrain a good text-based editability, because there's some trade-off curve when we move around in the latent space. But we can kind of cheat and avoid this by just not moving around in the latent space, but changing the latent space and the model itself, right? But doing this naively tends to cause catastrophic forgetting and leak the concept into everything else that the model can produce. So we can see this visually. If we take a model, right, we can take Stable Diffusion, and we can ask for oil paintings of cats and get results that look like this. Not bad at all. Now, we'll very, very briefly fine-tune our model on images of this cat toy, so briefly that it still doesn't manage to put it into most prompts, right? So if we ask for a photo of this cat on Mount Fuji, we'll get things that look like this, right? It started to capture the details, but it's not quite there yet. But even at this point, if we ask again for an oil painting of a cat, again, a general cat, not our specific cat, we get something that looks like this. oops, right? So we can see that even though we asked for a cat, we already have details from our own cat leaking into the rest of the model. And you can see that many of these examples here are no longer oil paintings, right? They started to capture the background of our images, things like that as well. And if we keep on training, this gets worse and worse. Things will no longer resemble oil paintings at all. And the model will just start outputting our original training images, no matter what prompt we use. Okay. How can we overcome this? Well, we've got two options. The first is through something called the pivotal tuning, which those of you who worked with GANs are probably already familiar with. The second is through something called the prior preservation loss, which was presented in Google's DreamBooth paper. I'll just mention briefly that both approaches do still leak some information, but they significantly reduce the leak. And let's say a few words about how each of them works. Okay, so starting with pivotal tuning, the idea here is to do our inversion in two steps. First, we can find a code, right? Let's say we want to invert this image of Michael Jordan, and we can try to invert it into an area of the latent space which is highly editable, right? Let's say close to the real words. This will hurt our reconstruction, right? We won't manage to get something that looks exactly like Jordan, but we can ensure that it exists in an area which we can later modify more easily, right? Change the pose, for example. Then we can fine-tune the model around this point in order to make the appearance better, right? To change the appearance in this specific region to match our target image better. Why does this preserve the latent space better? Well, simply because the model needs to change less in order to capture the details of the subject now, right? We started at a much closer point. We need less of a change in order to fix the smaller details. And in order to do that, we don't need to hurt the model as much as we would if we just started in some random spot. Okay. And we'll soon see a few examples of what we can produce by using this method. The second option is to use DreamBooth's prior preservation loss. And here the idea is that they basically add a loss that prevents the model from drifting too far by making sure it can still recreate images of the target's coarse class. Right? So if we want to train on this specific dog over here, we make sure that the text, a dog, can still recreate the same images that we could get with the original pre-trained model before we started to fine-tune it. Right? So basically, we're concurrently trying to reconstruct images of the specific dog and general dogs. Okay? And this makes it harder for the model to break apart, right? It makes it harder for the local region to change and for information to leak away from the prompts that have the token representing our specific unique dog. And you can really see in the results that they do indeed manage to preserve identity very well. So these sorts of tuning methods, they give you much better identity preservation. They manage to overcome a lot of this identity editability trade-off. They do come at the cost of higher memory requirements and much larger model files. For example, for stable diffusion, a DreamBooth model typically takes around 2 GB of data, and a word embedding is just 3 kilobytes, right? So there are some consequences for sharing these things, but I guess that's just another trade-off you need to decide on when you try to decide which method you prefer to use. Let me skip this one, it's not that important. Okay, so that's it for tuning, but we can also talk about a different way in which we can combat these overfitting, which is prompt weighting. And we're going to discuss 3 ways for doing this sort of manipulation, but there's really more and more of these methods coming out every day. So you can probably find many more, with simple web searches. Let's outline a few. And we'll start with the simplest one, which is basically saying, let's try to do an interpolation between different prompts at the output space of flip. So I guess that wasn't clear enough, but let's dive into it and we'll understand it better. Let's say we trained a token for this object over here, right? This headless statue. And then we try to get an image of it in the style of Picasso. But we see that the model didn't really quite manage to retain the object, right? This doesn't look anything like our target. What we want to do is to manage to put more stress on the object itself, right? And we can do that by using a two-part prompt for which the common implementation syntax looks like this. And what you see here is basically that we have two parts. One says a cubism painting of our token in the style of Picasso with a weight of 3. The second part is just a painting of our concept, again, with a weight of 1. And what the syntax means is that instead of using the single learned prompt, we break it into the two parts. We first encode only the first part, a cubism painting in the style of Picasso. We give it a weight of 3. We encode the second part and give it a weight of 1. And we just use this sort of weighted average in order to create our final conditioning code. Right? Admittedly, this doesn't make a lot of intuitive sense. If you recall, we mentioned that the output of the text encoder is actually a tensor of length 77, right, with basically a transformed representation for each word in the prompt. And since we're interpolating along each entry of this tensor, without any regard for the fact that the words in the different indices may have been different, we may have had, I don't know, this text is much shorter. It will have more padding tokens at the end. And we're interpolating between these padding tokens and the words in the longer prompt. So it's very strange. It's weird, but it works. So maybe someone will investigate this at some point and understand what's really going on here. But you can really see that it does give us a much better representation of our object as a Picasso painting. Another one that makes more intuitive sense is just swapping out the prompts partway through the prompt, through the denoising process, right? Diffusion is a multi-step cleaning process. We can start with our conditioning prompt and then just replace it at some arbitrary time step. So for example, here we have a painting of a general where we ask for a male general to begin with, and we can swap the word male for female partway through the process. And we can see that the earlier we make the swap, the more our image resembles a female general rather than a male one. Okay, so this is one way to try and balance between very strong prompts which overfit the model and words which the model knew originally, which won't cause as much overfit. Okay. Finally, the last method is something that is typically called attention weighting in the UIs that implement it. And what it does is basically it takes the conditioning vectors that we produce from the text encoder, and it increases or decreases the length of the vector in a specific words index, right? Again, typically at the output space of the text encoder. So for example, we can take this sentence, a photo of eggs and bacon on a frying pan by Greg Bukowski, and we can take the tensor entry, the conditioning code entry at the same index as the word bacon, and just multiply it by some scalar, right? Just increase the length of this entry. And what this does is it puts more and more stress on the word bacon and just adds more and more bacon to our generated image, right? And we can do the same with the word eggs, right? Just increase the length of the representation of the word eggs and slowly get more and more eggs in the image until there's basically no bacon left, right? So that's another way in which we can control the strength of our words, right? Just by multiplying their encodings by some scaling. Okay. Why are these methods interesting? Again, because they let us artificially increase or decrease the effects of specific words on the generated results. And this can let us handle overfitting with our learned concepts. So if we're back to our problematic cats, we can look at our poor image of a cat on the beach, but we can now try to apply some weighted prompting instead and get an image that looks like this. Right? It's a bit worse off on identity preservation, but it's more or less back to the level we had with LDM, and we finally do have a beach in our background. Okay. Here you can see a few more examples of these methods in play, including this cat bag over here, which is probably my favorite result of the whole paper. So I'm going to make it bigger so that I can admire it for a few more seconds. But that's basically it. So with that, we've reached the end. But before we get to the questions part, I just want to summarize the things that I hope you'll take away from this talk. So we saw some cool personalization results. I hope the applications of this path are clear. We also saw that training tasks matter when we try to learn representations. And we saw that even the text embedding spaces are very expressive. They can contain a wide range of concepts and really understand the semantics, right? But honestly, if there's one thing I want you to take away from this talk, it's actually this. Text gives you amazing creative freedom and great compositional understanding, but natural language it's limited. It's plagued by ambiguities. It's very hard to describe specific things, right? What we're actually proposing is to overcome these limits by combining two different modalities as an input, right? We use both vision and language, which lets us leverage the advantages of each of them and really lets us, increase the range of applications that we can tackle with these tools. Okay. So that's it. Thank you very much for listening. And if you have any questions, I'd be happy to answer